So I guess you guys have also, maybe there's also a lot of very good class previously, just like by Yang, by Jiantao, yeah, by a lot of other people in the class. So I'm thinking when I was asked to talk about this, I'm thinking about, okay, what I should talk about. So this is why I choose to talk about, okay, so probably I should talk about something maybe that's not shared in the textbook, but I think actually is what is really working in our daily work when we are training this kind of the large scale of the models. So my name is Weizhu Chen. So here's about me. So I'm an engineer. I'm also a researcher as well. So basically, I lead the Gen AI team and the co-AI, the post-training teams. So post-training for today, most of the effort is in the reinforced learning trainings. So I get my PhD in the Hong Kong UST and I work in the MSRA and I come to the US in the 2012. So basically, I've been in Microsoft for about 20 years and split between the MSR and the product team. But now actually I'm in the product team. And also because I'm more passionate about how can we build a product that's really working. And it's also interesting, actually, I found when I am in the product team, actually even my research actually is much more productive when you are in the product team today. So as you can see, most of the work here actually was done when I was in the product team. So yeah, so I think that's about me. And the next step, I think I would love to talk about, for example, just like use this as an example. So how can we build this kind of the agentic model? So my effort here today is more like about the model training instead of the model inference, because I still truly believe actually if you want to improve the model quality, you need this kind of the end-to-end training to make things happen to build the best models. So here it's just about an example of the coding agents. It doesn't mean we're just working on the coding, we're also working on something else. But I think coding actually is a really good example to share how the model was trained today in the industry. So because a lot of people here actually use the Visual Code, GitHub Copilot, Cursor, whatever. And for example, just like here is about one of the examples, just like you go to the GitHub, you have the GitHub issue, and you also have this kind of the code base. And basically that's your repository. So the issue basically you will describe, okay, what they want to solve. For example, this is the bug, I want to fix this bug, something like that. And that's in the laptop. And definitely here you have the model. Your model is going to try to solve these problems. But I think besides this, there's also a lot of other things here. One is about the environment simulator. So because you need to run the code, you need to run the test, and this mostly didn't run in your local machine. And actually it's running in a sandbox. So you have this kind of the very large scale of the environment simulator. So yeah, environment simulator, most of them actually is running on the CPU today. And so basically, but the number of the CPU here, definitely it could be at least 10x of the number of the GPU today. So that's also pretty huge today. And for this kind of the simulator, basically you can do a lot of things. And the most interesting thing is about the language model is going to communicate with the simulator to run so many different things for multiple times. And this is the multi-turn conversations. Basically, you can think about it this way. And finally, the language model will think about, oh, yes, actually, after I do all this kind of thing, I can generate something now to fix the issue. So you're going to generate a pull request, something like that. And this pull request is going to get back to the users. And the user will do continue interaction to say, oh, maybe you didn't give me the right pull request. I need to change something additionally. So it's this kind of the multiple turn conversation continually. So that is about a very typical agentic model training round. And definitely, there's a lot of other things. And they're also going to do the unit test during this kind of when the environment and the language model will ask you, okay, can you run tests for this? And then after actually, you're going to tell me so whether the test pass or not. So basically, for example, if you want to say about, okay, what is about the agentic training? Definitely, there are so many different things about the agentic training. But I think there's a few things definitely is very important. For example, just like based on the examples. One is about you need to be very goal-oriented. You have a goal you want to achieve, whether it's the math problem or whether it is about you want the model to generate the pull request for you. So that is the goal. That is the exact goal. And these pull requests also have a lot of requirements. Just like you need to solve the problem. You need to be able to pass all the unit tests or whatever. And basically, I think another thing is about the tool usage. And this tool usage, just like I mentioned, there's a simulator there. You have a simulator, and you want to ask this simulator to run a lot of things. So, and this tool usage actually is multiple turn. It's not a single turn. Actually, the communication is pretty complicated sometimes. And you also need to, the model also need to do the planning. And the planning means that actually the model need to decide, okay, what I should do first and second. And the model also need to reasoning, because actually the model is going to decide what I need to do next based on the current status, based on the current feedback, and including from the model itself or including from this kind of the simulator. So you need to do the reasoning. That's why, for example, you can see that the reasoning model is so suitable for this kind of the agentic model training. There's some reason there. So because the model really needs this, and also in a real system, actually, there's also need to consider is the user interaction. The model need to listen to the user based on the current context. So what is going wrong, what can be improved, something like that. And to achieve all this goal, there's so many things. But I think for today, I'll only talk about a few things that's pretty simple, because I think maybe this kind of thing actually is a little bit different than your understanding from some other place, based on my experience in the industry. So first one is the data, because I think data actually, nobody will underestimate the importance of the data. So we can also share maybe, for example, what we have done on the data side. So the other one is the grader, is the evaluation. So I think Yang in the first class already mentioned actually, reinforced learning agentic model training is more about how you define the evaluation, how you define the grader. But it's not that easy to define the grader. So, and the other one actually I want to talk about is about the efficiency. For example, because when you're running with these kind of thousands of GPU, the efficiency actually define a lot of things, whether you can run it very, very stable. And the last part actually I didn't mention here is I'm going to talk about also in this kind of direction, what is the next? What is the most interesting thing here? So for the data, so I think everybody know about actually we have two kinds of data. One is about the data, actually the result can be verified. We call it verifiable. So just like math, just like coding, you can run the unit test, just like STEM, actually just like the test, A, B, C, D, you also have the right answer. I think, in my opinion, actually this kind of the verifiable definitely is super good. So it's actually bringing in a lot of intelligence. But in the real product, a lot of things actually is non-verifiable. It's very hard for you to verify whether this is the ground truth or not. And it's pretty open. For example, there's so many different things. There's no verifiable, just like whether we show the code to the user, whether this code is in the good style. For example, just like whether this writing or this representation is in the good style, whether you like it or you don't like it, is very subjective, I want to say. So the other one is writing. For example, you ask the language model to write a poem for you or whatever for you. Different people have different opinions. So this is not very easy to verify the safety, or maybe this safe for him, but it's not safe for the other persons. So I think we already know about this, but I think there's also one of the things, there are two things actually I want to talk about today. One is called the rubrics. So that's how things work. Actually, in the industry lab, we build a lot of rubrics. And this is also something pretty special. Maybe I'm going to show you an example. So it's much more complicated than most people think. And rubrics, actually, we basically have a lot of very good people to write this kind of the rubrics. The other one, actually, I want to mention about is the data synthesis. So the data synthesis is so important when you're trying to run a lot of this kind of the product. So because the data synthesis actually is the most scalable way, you are able to synthesize the data. And at the beginning, maybe previously we think about, okay, maybe building data is just some dirty work. I want to share with you. Now I put the best talent in the team to build up the data. How to synthesize the data actually is the most important thing to make the model much better, especially for the model in the product. So for the rubrics, so let's say about, for example, I think the right side actually is the examples. It's an example for the rubrics. You can think about this is the questions. And actually the basic idea is about this is a question. You can also ask the human expert to write a ground truth based on their opinions. But I think this is not enough. This is previously, but now actually we want the human to write this kind of criteria. And it's no surprise to me, for example, for a question, there's 50 criteria. And each criteria, it need to be super clear. and very detailed, and human is able to read. And it's also very structured. It's also able to score it, to give a, maybe, for example, if you respond this thing, actually the score is 1 or 0 or whatever. It's able to be scored because the scoring actually defines how the reinforced learning, during the learning, actually how to run the grader. And this is going to be the input for the grader. And so basically this kind of thing is definitely this is super useful. For example, just for this kind of open domain questions and open questions, because it's really hard to measure. So what is the right answer or no? So if you're not able to measure it this way, so the way is to split into finer grain. And then for each of the piece, actually we measure, okay, this is good or bad. And we try to measure that. Because if you cannot measure that, you cannot learn. That's the most important thing. And the other one actually I want to say is about the effort to write down each of the example actually for today is very expensive. Sometimes for expert, they can spend a few hours or a few days just like write up all this kind of criteria. It's pretty normal. So it's not like just like write the ground truth anymore. And you need to be very comprehensive. For example, all the criteria I write up together is able to cover all the aspects. For example, for these questions, so whether it's able to really measure the answer. So because in this case, for no matter which kind of answer, you can use the rubric to measure how good is the answers. So, and the other one is about quality is more important. So most of this, actually, we don't need so many. We ask the language model to do a lot of generalizations. So quality actually is much more important than quantity. And for here, I just want to ask a question. We say about this is expensive, quality is important, but how many is needed? So I think a very extreme case is about how about we just have one single example. We just write one single example. Can we get the model to learn to a very good quality? Because when you guys do about this kind of the SFT, or even you use the thing to train a reward model, one single example is not enough, right? It's always not enough because it's very hard to say, maybe using one single example, but we do a work like this. Yes, we did do this work is about for the reinforced learning with the verified reward. If you just use it to train with one single example, what is going to look like? So this is for the math work. So because definitely this is important, but I think when we do the research, actually we use a public benchmark to verify a lot of things. So you can see that in the lab, this diagram, the interesting thing is about this one, actually the dot line is about based on the training from 1,200 examples. And for this green line, basically, it just use one single example. We just use one single example to train the reinforced learning. It's really one single example. We just keep working and keep trying to verify the answer, whether it's correct or not. And you can see that actually it can go up, it can keep going up. And finally, actually, it's very close to the pace. Actually, you used to train with more than 1,000 examples. This is very, very amazing, right? Because if you just use one single example, it means that actually, when you do the RL, it's really not trying to remember these examples. You try to understand actually how to solve the math problem. But the evaluation set have so many different questions. So the evaluation set is the same. And there is one example I want to say. I think the other point I want to make is about the variance. So how to pick this one single example is also very important. It doesn't mean that every example is good enough for you to train using one single example. Right? So how we pick the one single example here is about basically we try to calculate the variance for this example. For example, for this problem, we use the model to roll out whether they are very different or they're almost the same. So basically, we prefer the difference. That's we are going to talk about how can we encourage this kind of exploration. We want the model and the example based on this model actually have different kinds of the rollout in the reinforced learning. So because the more rollout you have, actually the better we can learn. We can observe for the model. And we can see that actually based on this, so there's one example based on this rating. For example, this pi 1 actually is much better than the pi 17. I'll just give an example based on the qualities. So this definitely tells us a lot of interesting things about reinforced learning. The RL data actually is very different than the SFT or the RLHF or the DCOM data. So I think the difference basically, it means the power of the exploration is different. Now, if you use this way, you have much more power for the exploration. You are able to explore much more. So we understand actually using this example, it's not just about memorizations. It's not just about you try to memorize this problem. Actually, use this problem to understand what is the building block for math, how to solve the math problem, just using one single example. And the second one definitely is about its extremely high data efficiency. There is a difference. For example, what the difference between RL today and what's the previous work is super high efficiency. If you're able to pick the right data, you have a very good learning policy. So, and definitely, as I mentioned about the quality really matter here a lot. So that is one of the first point I want to make. The second point I want to make, actually, definitely, in the industry training, you have so many different examples, so many different tasks. For example, just like what we say about when you train a code model, it's not just about the pull request. For the coding model, people also go there to ask a lot of non-coding questions, also ask a lot of question answering, right? For example, okay, can you write a document for me based on the code? So there are so many different kinds of data. So in the industry lab, actually, I want to say for the data work, it's not only about the source data itself. Most of the effort actually spent on how can we mix the data. For example, this data actually is 3%, data is 20%. So we just keep changing a lot of this kind of data mixing when you change the final model. And so the data actually is super important when you do the mix. And for example, it's also very different. You also keep changing the data mixing during the training. For example, at the beginning, we can put in a little bit more of the easier data to get the model learn to this level. The model can learn about this. But when the training moves forward, the model becomes stronger and stronger. Actually, you're trying to mix in more and more difficult data. That's also how a very basic thing we did. And so you can also try to combine more synthetic data. And for example, if you want the data, but you need this data. You know your model actually is very good in this 3 category, but it's not very good in the other 2 category. So how can you solve that? So the way to solve this basically is trying to synthesize more data. That's the most easy way. You can try to find more data. You can also, if you cannot find, actually you can do is the data synthesis. So that's why I mentioned about, besides this kind of the rubrics data, this kind of data efficiency, the second thing actually is the data synthesis. So data synthesis definitely it work. So for a lot of things, I will also continue to use math as an example when we do the publication, but actually, so math is just one of the work. For example, we try to say about, okay, is data synthesis just work to solve the data quality problem, or you can also trying to solve some other problem. So this is also another work is about, for example, for the math, actually you have the question, you have the answer, right? So can we synthesize more questions? So how can we make sure all these questions actually is the right questions? You also have the answer that's verifiable. That's a verifiable answer. So I think for the math and the answer, actually, we try to synthesize a lot of new questions. But we also have a mechanism to guarantee all these right new questions. The answer is verifiable. So this basically means that actually we increase the data diversity. We have more math. It's not like the original representation anymore, actually. We have a way to unlimited, I cannot say unlimited, to synthesize a lot of more data. And another interesting thing is about, for example, for the reinforced learning, we know that when we try to do the reinforced learning, there's also some kind of effect. It's about the entropy collapse. The entropy is going down, actually, when you're trying to improve the qualities. So we found that actually using the data synthesizer this way, it not only improve the entropy for the parsec 1, it also improve the parsec k significantly as well. So because sometimes you improve the parsec 1, but in the RL training, most of the time, actually, the parsec k didn't improve. But I think just like I mentioned, if you want the exploration, you need the improve of the parsec k as well. So sometimes we pay a lot of attention to the parsec K. It means that actually you just sample multiple answers, so any of them actually can give you the correct answer. So we found that data synthesis actually is also very powerful to give us a better parsec K as well. So you can go to read the paper, and I think that's also very interesting. The other one, because we talk about math, we also talk about the agentic task. So the agentic data actually is super hard to be synthesized. I cannot share how we synthesize that, but I want to share maybe, for example, the Kimi K2 actually also give a very good work. It's about how they synthesize the agentic data. So basically, I think the solution is also pretty simple. So it's just like the very typical solution. You need the existing data. They try to get the data from the GitHub. They try to understand, okay, this is a tool definition, because you need to synthesize so many different things. Data synthesis today is pretty complicated, I want to say. So basically, they synthesize the tool definition, this kind of the task, and all these kind of things. They also have the entire pipeline to make this kind of data synthesis to be runnable, to be scalable. So for example, they try to synthesize, they take some existing tool first. And they also try to synthesize some tool definition. And the task is also synthesized. For example, is which one you want to synthesize, and the agent is also synthesized. And after that, they mix the synthesized data and the original data together they get from GitHub, and to try to run this to train the model. So basically, you can think about the data. The one point I want to make here is that data synthesis is pretty complicated today in the industry. And for me, actually, I just put a lot of best people in the team to work on the data synthesis, because there's a lot of innovation there. So as a PhD student, and so I think data synthesis actually is super important. If I want to open a startup, I would think about okay, how can we synthesize the better data? Because the training approach will be converged much easier than the data part. It's so hard to synthesize the data, and unfortunately, a lot of industry lab, maybe they didn't share with you how the data was built. But I think this is definitely the most exciting part, and so for the data synthesis. Okay, so I think I finished the most of the part about the data. I think definitely there's a lot of other things you can get about the data. Yeah, but I think the other thing actually I want to mention is about the grader. So the grader basically, because we know about RL is about the experience. And the feedback, for example, can only be measured by the grader. So if you're able to define what is the grader for the problem, I want to say actually, at least you solve half the problem. So that is the point for the grader. So for most of our work today, every day, so it's figure out what to grade. It's not that easy. It's not just about the pass rate. It's about, for example, even for the coding, just like the representation, whether it follow the behavior, whether there is the product constraint. So every day, just think about, okay, based on the user's interaction, what is still missing? So based on this, actually, you understand what to grade. And we just add more and more grader. And so I think add more grader actually is not an easy task. For example, some grader is going to be conflict with some existing grader. You need to understand about how their relationship between multiple graders. And so that's the second part. The third part actually, what we do every day is about how can you, after you figure out, okay, what to grade, how can you prepare the data to be graded, right? So how can you collect data? So basically, grader sometimes it's just part of the data. So it's highly related. And for this kind of thing, if you want to build a foundation model, because we are also doing this kind of the post-training of the foundation model, so there's so many things you need to care about. So many different domains, just like medical, just like law, all these kind of things you need to be able to grade. And also, there are so many different problems. For example, even for the coding, there's so many different problems, just like next edit suggestion, just like code completion, just like coding agent. And so there's also another thing I want to mention. There's also a lot of product constraint. For example, just like, let's use the coding as an example, coding agent, because the customer like, okay, can you always produce some progress to tell me, because this time is pretty long, sometimes 10 minutes. And I just want to go for a coffee, I don't know, okay, how many more minutes you need. Can you tell me to share with me the progress? So this is some kind of thing we need to make sure actually the model is also able to generate something like this. That is the product constraint. It's not just about the pass rate, this kind of the single academic metrics anymore. Yeah, so that's what I say. I think I already finished this in a previous talk. Actually, it's about in the product, the grader is so complicated. It's not just about the pass rate. For example, there's a lot of Q&A questions. There's also a lot of multi-turn. How can you grade the multi-turn in this kind of the user interaction? And how can you grade the format? For example, there are some table, there's some markup language. You need to make sure actually all this is represented in the right way. You also need to solve the progress, something like this. You also need to make sure actually is the length is not too long. If you're able to solve the problem in the shorter length, actually, definitely nobody will prefer this kind of the verbals. And we also try to measure the time to the pull request. And so because it's the model cannot say something that's very bad as well. So that's all the thing actually you need a grader to take care of. So let's just use a coding as an example, because basically this is the thing actually everybody is using every day. So for example, we have the unit test grader. We also have the patch grader. We also make sure the format is right, I think. And all this kind of thing actually is trying to grade whether this is a good coding model based on the interaction. So if you want to summarize, for example, which kind of grader we use every day, this is the three most popular one. Just like I think the first one is very simple. It's just like the unit test. We call it as the verifier. You're able to verify actually this pass or no pass. And the other one definitely is we can use another model to do the grader. To use a large language model using the prompt or whatever to say, okay, so to give a score or something like that. And the other one actually is just like I mentioned in the data part is called, we based on the rubrics to do a lot of grading. So, and the other thing actually is just like I mentioned, when you're building a product, you will only put more and more grader there, right? So because you always want to make sure the model is able to have to solve some problem. So I think a lot of things here actually when you put more and more grader, it's super hard for any of the rollout to pass all the grader, especially at the beginning. The model is not capable enough. You want to say about, oh, for example, just like a kid for 3 years old, you want to ask them, okay, you need to follow the rule in the university. So actually, the kid don't know about this. So what we did is basically it's about, we didn't try to say about this pass or no. Actually, we try to do the ranking to say about, okay, this is better than the others. So, and based on the learning for these rankings. And the other one definitely is the curriculum learning. So for some grader, you can add at the end. You don't have to add at the beginning, because otherwise, I don't think the model can learn anything, because it's too hard at the beginning. So, and you also need to understand the grader dependency. For example, this grader actually have a dependent on that one. If you want to solve this one, you need to solve that one first. So there is kind of dependency, because some grader is more strict than the others. So that's also something we need to think about. And actually, you also need to think about the efficiency. For example, some grader, they need to run in parallel. So in this case, you can make the entire running much faster. And as long as you have the grader, you try to graduate something. So the model is trying to cheat something. It's going to, this kind of hacking, cheating, actually, based on grader is a pretty normal thing, because the model is so smart at this moment. And we also see a lot of surprise. For example, when the model trying to cheat, trying to do the cheating, because the model is really smart. For example, the model can remove all the test case. When you try to ask it, oh, you need to pass all the test case. Or the model can change all the content in the test case, just have the pass there. And so because, for example, for the coding task, some tasks actually, we also, another example, just like a task actually, we need internet access. For example, just like we use a sweep bench, verify this kind of the task. The model is very simple. They just try to go to the internet to find the right solution, and then to copy the right solution as its output. So I just want to say the model is so smart at this, and it's so hard to avoid this kind of cheating. So what we did actually is to avoid this hacking, cheating. I think it's the same thing. So basically, there's also a lot of things we did actually. We try to use another model to check the model, to check the model's output, to make sure actually it's not that easy to be cheated. And to use the model to regulate the model itself. We also check so many different places. So you need to be super careful. For example, when you try to train a model based on this. And for example, if the model is able to change the test case, we just hide the test case. We just remove all the test case. When you try to run in the sandbox. So, and then do the testing, and then after that, we patch the test case back. So for example, we also try to say, okay, if you're able to cheat, so I want to give you a very high penalty if you cheat again. So because sometimes it's so hard to, I think I just want to share there's so many this kind of examples when you're trying to do the grader for the RL trainings. It's not that easy. You need to be very, very careful. It's so easy for the model to cheat. Okay, I think that is basically about our work, about the data, including grader. So I think in our work, basically, we spend, I'm not sure whether 50% in our daily work is the exact number, but I think we did spend a lot of time in the data and the grader when we're trying to build a model every day. So, and the other part, actually, what we spend a lot of time on is the efficiency. Because I think when you're running this kind of the large scale system, how can you make it super efficient, as efficient as possible? And efficiency definitely also include how can you make things work? Because if it don't work, efficiency is zero. So that's the part actually I want to mention, how we do this today. So how to make the model more efficient, because reinforcement learning is so expensive. It's just like I say, so even for given one example, as long as you're able to give a lot of compute, it's able to learn a lot of things. I think it doesn't mean that actually a lot of compute is so easy to get, and it's so expensive. And this is not only about the GPU number, this also defines the iteration, the speed of the iteration as well. So, and because I think the model need to explore a lot, so what we did, and definitely I guess you know most of the industry lab, so there's a lot of this kind of asynchronous. Because reinforcement learning, you have the sampler, you have the trainer, if they need to wait for each other, they're super slow, especially in the large scale. So I think you can see a lot of people actually today is a lot of lab actually is using the asynchronous. So asynchronous is super important. How to make the asynchronous work is also not that easy, especially with scale. And the other one actually, how fast? It's just like, I think the one example learning is the instance for us to understand how important to enable this kind of policy exploration. How can you encourage the model to explore? I think that's also the most exciting topic, research topic for the RL as well. There's a lot of optimization work you need to happen here. How can we enable it to explore more? And so the third one actually is about how can we control the sampling cost, because the cost is very high. So we also do a lot of things to make the sampling cost much lower. So actually your entire job can run much faster. So the last one actually, how can we use LoRA in the RL to make things work much better or much more efficient? Okay, I think asynchronous I just mentioned. I think it's very simple. You just make it as a policy learning, and actually the sampler actually, because the sampler is the most slow part, especially when you need to sample the chain of thought, this kind of the long horizontal. So that's super slow. The sampler actually is much even slower than the chainer. Previously we say about, okay, the chainer is the most slow one, but now actually the sampler is the much more slow. Yeah, so and we definitely in our training we assign much more GPU to the sampler than for the trainer. So that is how we work. And how things work. So I think this is just a very simple diagram about this kind of asynchronous. Asynchronous, they mean that actually the trainer and the sampler, they don't need to wait for each other. You just keep sampling. And when you do the sampling, actually you don't need to be the latest policy. You just keep sampling and maybe use the policy in the last iteration. I think definitely here, there's a lot of work we need to do to make sure they can converge. It's not that easy. And also this kind of, yeah, so as you can see, basically, often we just have one single channel. But I think we have multiple sampler. We call it as roller here. You just need to roll the examples. So this roller actually is not only need to talk to the grader, you also need to talk to the environment. For example, to run a unit test or this kind of the simulator environment. The grader also need to talk to the environment if it need to do something. And so basically, there's some way to sync. Yeah, I think this is a very simple diagram, but to make this really work so well, especially with thousands of GPU, it's not that easy. There's a ton of work there. And because a lot of things can happen as long as the thing is asynchronous. Yeah, for the quality and the efficiency, this two is so hard to be balanced. So the other thing actually, besides async, I want to say for the reinforced learning, the thing is about how can we encourage the exploration, because the more you are able to explore, actually, most likely you are able to get to a better result. So during the training, we want to encourage this kind of exploration to make it actually the policy able to learn more. So here actually is what we did for the exploration. I can share a little bit. So yeah, if you want to get the model to be able to explore, I think there's a few things that's so important. One is about the model need to understand, need to be able to follow the instruction. So sometimes, for example, you say, oh, this model is not able to produce a good result based on the reinforced learning, based on the RL. A lot of things is because this model is not able to follow the instruction. If the model is not able to follow the instruction, it's very hard for you to do a lot of things. So in that case, you need to continue to train the model to follow the instruction first before you run the RL. That's also one of the things we learned. There's also one of the things actually, for example, when you see the small language model is not able to produce a good result based on the RL, so I think the first thing to check is about how good is this model in following instruction. So that's one. Because why I want to follow the instruction? So one of the things, for example, we say about the prompt, how can we prompt the model? Because you can prompt the model in a different way. You can ask the model, oh, you can use this method to solve this math problem. You can also use another method to solve the math problem. So I think this kind of the prompting approach is very naive, right? But it's very, very important. There are so many things you can do in the prompt. You can even ask another model to generate the prompt. So because if you're able to generate have a good prompt, trying to prompt the model in a different way, and the model is also able to follow the instruction. So this actually gives so many different diversity for the model to see the problem in a different way. So this means that actually the model has so many different ways to run the exploration. The prompting actually is super important. It's not that easy. How to build up the prompt. If you're able to make the prompt much better, there's so many ways you're able to improve the models. So definitely, the other thing actually, we also want to control the length. We don't want the model to produce unlimited. And so there's so many ways. For example, you can introduce some noise to do this kind of exploration. You can also set up some different kinds of tools. Just like you can try this tool with this for the first time and try another tool set for the second time. And we can also rid of some tools. So to encourage the model to explore in different kinds of the environment. So that's also another way for the exploration. So the exploration. The other thing we face actually, because we know about reinforced learning, there's tool usage. But the problem is about now today, the user is able to hook up with any of their own tools when you try to use the model, right? You can use the MCP, you can use the hook up with your own API, and so how can you make the model to learn for different tools? Because the model, when they train the model, we don't know about which tool the user is going to use. We have no ideas. Yeah, but there's only one single model. You can hook up with so many different tools. I think the key problem is about how can you do this kind of tool generalization? How can you generalize the tools? So that's also one of the very important things. And definitely, we also did a lot of things. But I think the first thing is still the instruction following. The model needs to have a very high instruction following capability if you want the model to adapt to different tools. And the second one definitely is about the model can use the tool in the wrong way during the rollout, but it needs to be able to correct itself. The model needs to reflect, oh, if this cannot solve the problem, can I try different tool? And also, this kind of when you train the model, you need to fit the model so many different kinds of tools. And we make sure the model is able to use the tool in the prompt. It's also part of the prompting. If the model didn't use the tool in the prompt, you specify it, you need to give the penalize. So yeah, you need to try to say the model, actually, you are not doing the good work. So that's also part of the grade as well. So the other thing, actually, as we know about the efficiency, is about the solution length. Because as you know, the bottleneck is in the sampling. But the sampling, the thing is about the model will keep just doing sampling. The model is so smart, okay, if this cannot solve the problem, I just try again, and the model will just keep doing. And here actually it is more likely to solve the problem. But I think actually this is, the user experience is no good. For example, if the same problem, and actually one solution can finish in 1 minute, the other one actually need to finish in 1 hour. Definitely you will prefer the 1 minute one. So this definitely we need to have a balance between this kind of the performance and the cost. And so we did a lot of things to achieve this. For example, we can ask the model to solve the problem with different kinds of constraint, length constraint, and we always prefer the one with shorter answers. So that's one. Yeah, so but the thing is about, this is always a balance. If you can know, if the cost penalty for the length actually too low, the model could use unlimited tokens. For the reasoning model today, it just keep doing until you get to he thinks a better answer. But the cost penalty is too high. So basically, actually, you also sacrifice the exploration for the model because you don't encourage the model to explore a longer solution. So this actually is one of the challenges in our task as well. So our solution is also pretty simple. So basically, for example, here is the one you didn't control the length. Here is the one you control the length. So in the training, definitely we want to keep the very long rollout. If the rollout is about, for some rollout is 30 minutes or 1 hour, so we say, okay, no, we just give up. It's you need to have this kind of mechanisms. So definitely you need to have the token cost. This is pretty straightforward. It highly depends on the number of tokens. And in the evaluations, I think this is more interesting. For example, just like when you guys go to see the sweeping to verify this kind of the leaderboard, that leaderboard, most of the people just report the pass rate, right? They didn't report how long is the rollout. But I think this has the problem because actually this highly depends on the quality in this kind of the test time scaling. The quality highly depends on the length, highly depends on how much compute we want to give in the test time. So in our internal evaluation, we not only care about the quality, we also care about this kind of the rollout length. So we want to, in our opinion, actually a lot of things are not comparable. If their rollout length, if the test time is not in the same level. So that is also what we did here. So there's also a lot of other things, for example, just like the long context. So even, for example, there's some model is able to support up to 1 million tokens. But there's a lot of case actually, so even 1 million tokens is not enough. So, but today actually, for most of the model is 128K. So about 128K is not enough because the user will just keep doing and the rollout can be very long. And for example, for the coding part, some file actually can be also pretty long as well. So, and I think the solution here, so I just use the open source solution to mention how they solve the problem. So it's also very basic. This is the paper from Alibaba. It's called the RISC-SUM. Basically, it's about for any of the rollout or in the history, this kind of the early rollout, they can try to summarize it. After they summarize that, the summary is always much shorter than the original text. And they just use the summary to replace the text. And so in this case, they can keep working. So I think the idea is actually very simple. And this summarizer actually is also a totally separate model as well. I think in the real implementation, because as you know, the detail is all, yeah, so there's a lot of detail and there's also many different kinds of implementation. Whether you want to summarize the entire history or just want to summarize the COT, or you want to keep the original answer there, or you want to keep all the things you show to the user there. So I think there's a lot of detail for different implementations. But I think this can only, yeah, you can only evaluate this when you run the experiment by yourself. There's so many different ways to do the summarization. So the other thing actually we mentioned a little bit is about is about LoRA. Yeah, so, and especially for the LoRA on the reinforced learning. So I think one of the things, for example, I guess maybe a lot of people know about LoRA. And there's also a very good work from John, actually, is the LoRA without regret. That's also very important work. So I think they give a very beautiful work how to make LoRA work without any regret. So yeah, definitely, I would love to promote the LoRA work. But I think the other thing I want to, we also have a lot of discussion is about why LoRA actually can work in the reinforced learning training. Because we know about previously, LoRA actually works sometimes, and sometimes it didn't work. It didn't know as good as the full fine tuning or something like that. But I think the answer I try to give is about, I think LoRA actually is more about the regularization. Because basically, LoRA basically born with the regularization. For example, the main way is keep fixed. The main way didn't change. So the change actually in terms of the way is pretty small, no matter how we did this. So, and in the reinforced learning, definitely you need much more regularization than the SFT. For the RL, you don't want the policy to move away from previous checkpoint too much. That is one. The second one, especially for the op policy chaining, you always need the regularization. Because if the policy used for the sampling and the model used to change the model is very different, it's very hard for the convergence. So this op policy learning also need a lot of regularization. So definitely, that actually is I think it married the LoRa update very well. So that's why LoRa is so popular in the reinforced learning. So the other thing actually, definitely, there's a lot of other advantage for LoRa as well, just like have less number of the GPU. You don't need so many GPU. And also more efficient. You can train a little bit faster. So that's one. The second one I want to mention is not just about LoRa, it's about in the industry lab. For most of the GPU was used, we call it as the running a lot of this kind of experiment, just like this kind of data mix or that kind of data mix. Because everything is a trade-off. We didn't always say about, okay, we want to get to the best setting. We didn't use the optimal setting. Instead, we want the most efficient settings. Even the quality is the 1 point less or 2 point less. But we can run this experiment 2x faster or 3x faster. So what we did is about, we take this kind of the much more efficient suboptimal setting and put this as the baseline and put this constraint. And actually, we compare all this kind of change. We make all the change based on this constraint, and then we just do this kind of the side-by-side comparison. So this actually will make our innovation run much faster, 2x or 3x faster. I think that's pretty normal. And maybe after you figure out all this kind of the recipe, in the final run, you can run it much longer. You can take all the best settings, but I think previously, actually, we didn't use all the best settings. So that's another thing. Maybe you guys will feel surprised why we didn't use all the optimal settings, because it's too costly. So yeah, I think that basically is about capture most of the work I want to present today. I think actually the other thing I want to mention is about, because I've been working on pre-training, post-training, and listening, I'm also working on the reinforced learning. I try to think about, okay, for example, if I want to try to understand this and explain this to my 11 years old, because my daughter actually 11 years old, she loves to play Lego. And there's one line actually I play Lego with her. And I try to map all these kind of the most important concept into Lego play. So what is pre-training? So basically, pre-training, they give you a lot of data. And this data actually, there's no order, right? You don't know what is the order here. So we try to figure out when you play Lego. So for the pre-training, it's about the pre-training, they want to change the thing without order into the thing with order. So what do we mean with order? Actually, here I try to say about pre-training, you try to learn the I call it Lego piece, the Lego brick, the Lego block. They try to learn this kind of the Lego block. And there's so many of the Lego blocks, just like And they want to use this Lego block to simulate the original data, to simulate the wall again. So to build the Lego wall, actually, this is the data. But I think after you make this kind of change, actually, this is the order. So because they know, okay, this wall representing the data is built by a lot of different kinds of the structure Lego block, the Lego bricks. So I think that's how I try to explain this to my 11 years old, what is pre-training. So what is pre-training? And especially for pre-training, for example, when we compare a good model or an even better model, an even better model basically is trying to say about it can build much more complicated Lego block. And you also have a much more efficient way to assemble the Lego together to build up this kind of new Lego world. That is the better pre-trained models because you always need able to learn something that's much more complicated. The shape is much more complicated, so you just need smaller number of the pieces able to build up this kind of world together. So the pre-training definitely is also very simple. So basically, you want which kind of the Lego world you want it to be. So that is the goal. And that's your task. You just put all the pieces together to build up this kind of the Lego world for you. With the pre-training, actually, the Lego piece is already there. So that's why actually pre-training with the pre-trained model is able to help you to do this kind of pre-training much efficiently. So what is reinforced learning here? Reinforced learning, they basically is a learning concept. It don't have to be attached to pre-training or post-training. There's already a lot of work actually is also working on reinforced learning for the pre-training. So the RL basically is just about, it just create millions of this kind of the Lego world or maybe Lego game or whatever, and just get the feedback. With the good feedback, you say, okay, I want to build a world more like this. And without this feedback, the bad feedback, okay, this is not a good world. I just want to destroy and use this kind of brick, Lego brick to build a new world again. So that is the RL. It's just about you're able to figure out this feedback and to build up these things again. And one of the things actually I keep thinking about, can you do something new? Maybe totally different than the world today. I think it's possible. Because this exploration, maybe for example, just like if you go to the level world today, you will see, okay, most of the shape actually is that we can find in the reality. But maybe in the future, maybe there's always something new actually you cannot find in the reality. That need to come from, as long as you have this kind of very different block, is able to build up something, yeah, based on its imagination or creativities for the model. Yeah, I think that is about, I want to say, okay, so look ahead. Look ahead to me is also very simple because I only have two kinds of the things. One, the only thing common is scaling. So what we do definitely is the first one, definitely we need to do the testing time scaling. For the testing time scaling, basically there's only three things. So when you try to map all the activity, there's only three things. One is definitely is the deeper model, a more even larger model. Especially, I think for the reasoning, the model need to be deeper. So a lot of effort, for example, just that recurrent work recently, actually, is just trying to have a different way to make the model deeper. It's not only about, yeah, I think that's super important. Any way to make the model deeper, actually, it can help the reasoning. That's my point. So the other way is just like you grow a neural network. You either make it wider or you either make it deeper, right? You want to make the model more powerful. Definitely, there's also a lot of things you can do in the architecture. So how to make the model wider? Definitely, there's also a lot of other things you do become the parallel thinking. Just like you can do the parallel thinking. You can put multiple ways to do the parallel thinking. But I want to say one of the important things is about for what we do today, this kind of parallel thinking basically is just about you do it after you change the model. After changing the model, you just get the model, produce multiple results, and then do the voting or use another model to pick it. You didn't think about how can we consider this during the model training. I think that's also one of the interesting topics. It's not just about the testing time. For the training time, I really know, okay, for this model, I just want to use it to do the parallel thinking. It's not just about to get a single result, but how can we do this? I think there's definitely a lot of research thing here. The other thing to do the wider, I think is also pretty simple. You just maybe give it to multiple agents, and so multiple people to do the same work for you, and you see, okay, let them coordinate together. You also have a orchestrator or a boss or something like that to ask a lot of people to work the thing for you, and we can assign the task to them. I think that's also another way to make it wider. And beside the wider, it's also the same. The other direction, the other dimension is the longer. You want to make the task, the agent is able to run much longer. For example, for today, just like the coding, you just get the result in a few minutes. But I think maybe in the future, actually, you can ask to do a much more complicated task. It's able to give the result back to you in 1 or 2 days. I think that's also pretty normal. But I think here, actually, there's a lot of things. Definitely, it's a lot of research topic here. For example, how can we solve the long context? How can we try to memorize the behavior previously? It's not that easy. You want to memorize the behavior from 1 day ago or something like that. Human is very good at this, but model is not that good. So there's a lot of things we need to do here. So the other thing beside the testing time scaling, so I want to say the other thing actually we spend a lot of effort in the team is about the training time scaling. Training time scaling, definitely. And the first one is still the data. Just like I mentioned, we put the best people, best talent in data synthesis. I think that there's still a lot of things to do the data synthesis. It's not, they're just getting started. It's not the end of the story. It's just the beginning of the story. And because for today, you can see that we are often limited by the data instead of the compute. And how can we make the data more efficient? And we have a lot of compute, but I think we are running out of data. There's not much data we're able to leverage to boost the model to another level. So, and I also think about the best model definitely should be built from the best data. For today, to define the model, basically, I think at least more than half is based on the data. So for all this kind of industry lab. So agentic data actually make this data complexity into another level, I want to say. It's much more complicated. And how can you use multiple agents to synthesize the data? How can you synthesize this kind of long horizontal data? They're so complicated. There's still a lot of things to do. How can we synthesize agentic data? That's why I present this kind of Kimi K2 paper. I think they do a very good work. Yes. So reinforcement learning. And reinforcement learning, definitely. So at the beginning, when I tried to think about the RL, I think it's also pretty simple to me, beside that example. I think reinforcement learning, for example, if you compare to the SFT, just use the compute to check for the robustness. For the model, for today, so in the industry lab, basically, it's not only about the RL is able to make the result a little bit better, it's able to make the result much more robust. Because it's not just about the benchmarking. It's also about, okay, for example, when the user try to use another way to ask the questions, actually, you're able to produce the okay result. But SFT is very hard sometimes. That's why we use the RL so popular. And actually, it uses a lot of compute, much more compute than the SFT, but it did produce the robustness. That's super important for a product. And another thing, actually, the second point is about for the RL. I truly believe, actually, when you change the RL model, it will make everything right. It just keep going. The quality will just keep going when you feed it with more compute until it reach the model's limitation. So that's also very exciting because we found a way, actually, we're able to give it the compute, the model is able to become better. So there's no even better way than this. This is one of the big challenge problem. How can you make the model better with more compute? It's no easy problem. For pre-training, it's not able to do this sometimes. And it's also limited by the data as well. It's just like, another thing I say is about for the RL, where I put a lot of effort in the RL is about, it's easy to, it's more about the steerabilities. You're able to guide the RL into the direction you want. This is also very different than the ILHF. You train a reward model, or SFT is so hard. If, for example, in the IL, what you want the model behavior to be, you just define a new grade. It's so flexible. So that's why we love RL in this kind of product settings. For example, you just say, oh, you don't do it this way. You just need to change the grader to say, but if you do this way, that is the bad reward. If you do the other way, that is the better reward. So it's more about this. Yeah, so and it's just like I mentioned, we talk about pre-training, we just talk about post-training. I'm not sure whether now actually in the academic there's a war, or maybe in the real setting, okay, there's a pre-training team, there's a post-training team, and you just pre-train the model and then give it over to the post-train model. But there's a war between them. I'm not sure whether this war is really necessary. Even everybody talk about, okay, pre-training is for the compression, post-training is for the behavior. But I guess maybe I want to mention actually, RL actually, it didn't just stick with each side. Maybe in the future, there's only two kinds of loss. One is the reinforced learning, the other one is the next token prediction. They're just combining together to remove the war between pre-training and post-training. That's also possible. But let's see, I also don't know. And there's also last thing actually I want to mention is about in the future, the best way is the model is able to improve by itself. This kind of self-improvement actually, I think now the model is very powerful, it's become possible. And a lot of this kind of frontier lab keep working on this because if you're able, there's another way. So in the higher level compared to RL is about if you're able to put more compute and more data to the model, it's able to keep improving. And in here, definitely the data in the reinforced learning, actually, you want to achieve the self-improvement, you need to think about how can you build the data, how can you make the RL into the game. So I think that's the two piece most important to me. And definitely the model also need to be able to do the self-reflection, able to understand what is going wrong previously and to fix it. And also the other one, actually, I think a lot of things, if you want to make this, it means the previous iteration of the model is now as good as the next iteration of the model. So the weak learner is able to produce a better learner. So I think that is also one of the, we need to figure out the methodology about this. Yeah, I think this is actually, it's maybe not related to this task. I think it's related to our daily work. I think it's also some of the comments is about how can we change the model, because I know so many people change the model here every day. I just learned from you guys, okay, you work until 5 a.m. last night. So I think changing model actually is pretty hard, to be honestly. And because you need to often to wake up at 3 p.m., 3 a.m., figure out, okay, there's something wrong, to restart the job, and then to discuss with the team, actually what's going wrong here, and how can we fix to immediately, quickly relaunch the job to save the GPU. So, and you also, I think one of the things actually, I didn't mention a lot, but it's super important to us is the infrastructure, because there's a lot of things I cannot share in the infrastructure side. But I think that actually is another biggest pain in the reality, because infrastructure, as long as this kind of large scale, is not so stable. And you will pretty struggle. For example, when something is not stable, your job, okay, this GPU fail, that GPU then now actually lose the connection. There's so many things actually in the infrastructure, you are very struggle. I think a lot of time actually was spent in this kind of the instability of the infrastructure. And you feel very hopeless sometimes. Why this info? How can I train this model with given this info? And you also, because there's a lot of things. For example, training the model is about 90% of the time actually things is not working. For the 10% of the time things is working, it's really making the progress. This means that it's bad. 90% of the time you are not making any progress. You need to be patient. So that is why training the model is so hard. But on the other hand, training the model is also so fun. I think maybe that's one of the best jobs in the world. So yeah, we are so lucky. We still, we're able to have the opportunity to train the model, and because with so many this kind of GPU, and also you also really feel the fulfillment when your model you train actually is able to pick the baseline. Yeah, so I think that this kind of fulfillment, this kind of joy is not that easy to get from other places, because the baseline actually is the best model in the world sometimes. And so, and because I'm working on the product team, so if your model is able to use in the product by so many different people and collect the feedback, that's also another kind of the fulfillment as a researcher or as an engineer.